Today I'm very privileged to introduce speaker, David. David was an undergraduate at the University of Chicago, and then as a graduate student, he was here at Berkeley, starting in the late 1980s and 1990s. He was a brilliant student, and I was very privileged to be his thesis scholar. After getting his PhD, he was postdoc for a few years here in my group, and then went briefly to Amherst, and then almost immediately to Yale, where he's been since. And now he's a professor of physics. Without any doubt, he's one of the most distinguished experimental physicists in time. And his title today is Electron Moments, a tabletop scale code for PhD physics.
Thanks very much for the introduction. It's a real pleasure to be here. I spent a long time at Berkeley, but now it's been a long time since I've been here. So it really feels like a homecoming. And I just can't be here and give a talk without pointing out, that everything you're going to hear today, I can really trace back the intellectual roots of it to the guidance that I got as a student, as a postdoc. Of course, from Gene, who's just an amazing mentor, as can be seen from the success of his students, but also Maxwell Latoriev and Dima Butker worked alongside me in the lab for quite some time, and everything I didn't learn from Gene, I learned from these guys. So it's really nice to be back in the home nest again. So as Gene said, what I'm going to be telling you about today is an experiment that I started working on this problem as a postdoc with Gene, and I've been working on it ever since then, looking to see if the electron has an electric dipole moment. So I'll just start with telling you about how this phenomenon of electric dipole moments is related to particle physics and new physics beyond the standard model. Give you the basic idea of how we go about detecting the electric dipole moment, and then tell you about the specific experiment, the ACME experiment that we completed the first version of last year, and put a new upper bound on this, and then tell you a bit about what it means and where we go from here. So the place to start with this is the realization that I think most everyone knows that the standard model of particle physics is in some sense completed, in the sense that all the particles and forces that are needed within the framework of the standard model have been discovered and characterized, but it's still incomplete. There are lots of physical phenomena that we know are true about the universe, but are not explained within the standard model. For example, we don't know what dark matter consists of. This is a famous and well-known problem, maybe slightly less known, but still a very deep problem is the matter-antimatter asymmetry in the universe. So again, here the idea is that the naive expectation is that after the Big Bang, there should have been equal amounts of matter and antimatter created, and then the matter and antimatter should have re-annihilated and turned back into photons. But what we see is that in fact, the universe is made mostly of photons. Most of the entropy of the universe comes in the form of photons, but there's a little bit of matter left over and essentially no antimatter. And the way that things evolved from just after the Big Bang to now remains quite a mystery. How did the matter manage to survive while the antimatter has gone away? And of course, there are many other mysteries that can't be explained within the standard model, but these two have some relevance to their electric dipole moment, as I'll explain. What we're looking for, this electric dipole moment, the way to get the first handle on why this might be something exotic and interesting and relevant to particle physics is to realize that if a particle has a permanent electric dipole moment, then this will violate controversial symmetry. So let's start with a sort of cartoonish heuristic picture of an electron as a ball of charge that's spinning around some axis. Imagine it has an electric dipole moment aligned with the spin axis. You might ask what would happen if it was pointing in some other direction. From this cartoonish picture, you would say that the transverse components would average to zero as the electron rotates. From a quantum mechanical point of view, you would just say that this is the only direction that there is that you can associate with the electron. At any rate, if all electrons have an electric dipole moment in a particular direction along their spin axis, sort of pictured in this cartoonish way as a dent and a bulge along the spin axis, then if you take electrons and perform a time reversal transformation, then the rotation direction changes sign, the spin vector reverses its direction, but the electric dipole moment is just a static charge distribution. That doesn't change. So if all electrons look like this, then this picture doesn't exist, and time reversal is not a good symmetry of nature. So if the electron or any particle has an electric dipole moment along its spin, then time reversal symmetry is violated. And of course, a feature of quantum field theory, of all quantum field theories, is the combined symmetry of CP and T, charge conjugation, period reversal, is a good symmetry in quantum field theories. So within quantum field theory, which as far as we know explains everything down to the energies we're able to probe, T violation is equivalent to CP violation. So I use these two terms interchangeably. And it's been recognized in the particle physics community for some time that CP violation, or equivalently T violation, is really a very powerful and interesting new window into exploring new physics at high energy scales. So one thing to realize is that T or CP symmetry is a broken symmetry. The violation of these symmetries has been observed in K and B meson systems for decades now. So that we know that we can't simply say this is a good symmetry, it's likely that it'll be preserved forever. It's already broken. Once the symmetry is broken, it's likely to be broken in other places as well. And just as a quick reminder, time reversal violation from a mathematical point of view is always associated with some complex phases in the theory. So I'll mention these complex phases at various points in the talk. These observations in K and B mesons are all entirely consistent with the standard model. They arise from the CKM matrix that describes mixing between the quark flavors. And all of this fits into the standard model nicely. It requires the one CP violating phase that appears in the standard model to be of order 1. In fact, it's very nearly 1 radian. But nevertheless, the observations in the K and B mesons, despite the fact that they've been done for decades now, it's hard enough to interpret what's going on here, that there's still plenty of room for new ways of violating time reversal invariance at other higher energy scales. And it's worth mentioning that this particular way that CP violation enters the standard model through one case, here it is in the CKM matrix, is a very peculiar mechanism. So almost any particle theory that takes the standard model and extends it, adds some new particle content, it's very typical, almost unavoidable to include new sources of time reversal violation. It's really ubiquitous in quantum field theories that extend beyond the standard model. So it's hard to get rid of this. And in addition, in most of these extensions to the standard model, theoretical extensions, the existence of new sources of T violation can be seen not as a problem, but as a feature. And the reason is that it's been understood since the 50s from an argument from Sakharov that in order to explain this matter-antimatter asymmetry that I mentioned before, an observational fact about the universe, you need CP violation to do that. And not only that, but you need more CP violation, some different way of violating CP that exists in the standard model. The standard model violates CP, but at a level that's not sufficient to explain the magnitude of matter-antimatter asymmetry. So new theories that include new sources of CP violation, it gives you these theories the opportunity perhaps to explain the quantitative magnitude of the matter-antimatter asymmetry. And this is, I would say, a significant part of the motivation for looking for EDMs is that if we can find evidence for new sources of CP violation, that may give us a key to understanding this matter-antimatter asymmetry. That sort of sets sets the stage for why it might be interesting to look for an electric dipole moment. But the next question is, how big? How sensitively do you have to look in order to have an interesting level of sensitivity? It might be that, that any effect of this type would be impossibly small, but it turns out that's very much not the case. And in particular, I'll try to just recap quickly the arguments for why we might expect, and there's been a very widespread expectation that there should be new physics happening, not at just any energy scale, but specifically at the energy around the electroweak scale, EP scale or below. And just quickly, there are some very general arguments for why it's attractive to have dark matter made of particles whose mass is on the order of the electroweak scale. It's been recognized for some time that if there are new T violating or CP violating forces at the same scale of the electroweak scale, then these are capable of explaining quantitatively the matter-antimatter asymmetry. So you can kill two birds with one stone if there's new physics at this scale that also includes new CP violating interactions. And then there's also what's known as the hierarchy problem, which essentially says that it's natural that there should be some new particles at around the mass of the Higgs, which has now been measured. It's known to be around the electroweak scale. That in order to keep the Higgs mass from being unstable to radiative corrections, it's natural that other particles existing around the same scale can solve that problem. So none of these is anything close to an airclad argument, but they all seem to point in the direction that it's natural to have new physics at energy scales around the electroweak scale. So let's see how that adds up to an electric dipole moment, which is conceivably observable at a level that we're now reaching with our experiments. So now we have to understand how does an electric dipole moment have to do with new physics and new particles. So the place to start with that is to recall that in the context of quantum field theory, an electron is a structureless point particle, but it always has, again, heuristically, it's surrounded by a cloud of virtual particles. It means there are radiative corrections that are important. So everyone is surely familiar with this sort of Feynman diagram that describes a radiative correction, the virtual absorption and re-emission of or emission and reabsorption of a photon that corrects the magnetic moment of the electron, causes its G factor to not be exactly 2. And there are higher order diagrams or exotic diagrams like this that give higher order corrections to G minus 2. In general, for those who aren't familiar with quantum field theory, for these sorts of diagrams, heavier particles give a smaller effect. It scales like 1 over the mass squared of the particles that appear in these loops. And more loops corresponds to a higher order perturbation theory. This is first order perturbation theory. This is second order perturbation theory. So the electric dipole moment is another sort of radiative correction. It's one that has to involve CP violation or T violation, as I explained. But because there's T violation is part of the standard model of particle physics, in the standard model, the electron has an electric dipole moment, which is not 0. And this shows the lowest order Feynman diagram that can give rise to an electron-electric dipole moment in the standard model. You can recognize immediately this is a 4th order perturbation because there are 4 loops in this diagram. It's a small effect because it involves heavy particles like W bosons and top quarks. And then what's not so obvious is that due to what's called the Jim mechanism, when you add up all the 4th order diagrams of this type, they largely cancel each other. So the net effect is in the standard model, the electron has an electric dipole moment which is not 0, but it's fantastically small, too small for us to hope to see in any experiment that's been conceived of. By contrast, in theories that extend the standard model, things, for example, like supersymmetric models, it's quite easy to have diagrams like this one, a first order Feynman diagram. So first order perturbation theory that can give rise to the electron-electric dipole moment. And if these particles have a mass which is around the electroweak scale, then this first order diagram can give rise to an EDM which is big enough for us to see. In fact, much larger than our sensitivity, as I'll show later. So to get a sense of that, you can do a sort of dimensional argument for how, if you have a Feynman diagram like this with some new heavy particle, some T-violating phase and some coupling of this particle to electrons, how big an electric dipole moment would you see? The typical sort of assumptions that are made in the simplest minded theories are these couplings are not much, no weaker than electromagnetic coupling. This phase is of order unity because the only CP violating phase that we know of in nature is 1 radian. So that seems like a reasonable size for a phase. And if these new particles are at the electroweak scale with a mass of 100 GeV, you can write down the simple sort of dimensional estimate. You see it scales like the inverse of the mass squared of this heavy particle. It depends on the particle phase. It depends on the number of loops that are in the diagram. I've shown a 1-loop diagram here. But with these very simple assumptions, which would be typical for a generic extension to the standard model, you find that you would expect an electron-electric dipole moment which is already 100 times larger than the previous limit before our experiment, the limit that came from the experiment that Gene led and I had the pleasure of working on as a postdoc. So what this is telling you is that even before our experiment, electric dipole moments were causing trouble, were difficult to avoid, or theories had to contend with the fact that they hadn't shown up yet, even in previous measurements. Right. So this plot shows on a logarithmic scale predictions for the electron-electric dipole moment. For historical reasons, we tend to use these units. A dipole moment is a charge times a distance. We use units of electron charge times centimeters. This shows possible values for the electron EDM. This shows the limit from the beautiful experiment that Gene and I and many other coworkers over the years concluded in 2002. And this set the best limit for nearly a decade. It was slightly improved on by some competitors at Imperial College in 2011. But you can see, for example, the predictions of naive supersymmetric models were already thoroughly ruled out even by this experiment. But particle theorists are inventive and numerous, so they said, well, our naive expectations clearly were wrong. Let's make more sophisticated models that predicted electron EDM, which is just below the current limit. If you look a little harder, surely you'll find it. But in blue here are variants of supersymmetric models, but the generic feature of most of these bubbles is simply that there is some new physics around the electroweak scale and that there are T-violating phases which are of order unity. You notice there's a scale break here. The standard model lives over here, some 13 or so orders of magnitude below the previous current limit. And there's one variant of supersymmetry which also can not turn on an electric dipole moment. But in general, the sense in our community has been that being able to push the sensitivity on these experiments really has substantial discovery potential. It really pushes into very new territory in particle physics, and very generically is pushing to mass scales well above the electroweak scale, as long as the new theories include CP violation. So just to give you a sense of, as I start to describe these experiments, how challenging they are. Our result from the ACME experiment was featured on the cover of Science magazine. You know, this is some artist's impression of what an electron with an EDM would look like. And the main thing to take away is this resembles zero very closely, because the effect we're looking for is really tiny. And just, again, to get some sort of a scale, if you go back to this heuristic picture of an EDM being an electron with a dent on one side and a bulge on the other, and think about how large is an electron. Of course, in quantum field theory, it's an absolute point particle. But the radiative corrections, the photons, virtual photons around an electron, there's a natural size scale associated with those. It's about 10 minus 13 centimeters. So if you think about scaling that up to the size of the Earth, and then think about the previous limit size of the EDM, 10 to the minus 27 centimeters, then that would correspond to, scaled up to the size of the Earth, about 200 nanometers. So the equivalent of taking a 200 nanometer slice off the southern hemisphere and putting it on the northern hemisphere. So that gives you a sense. These experiments are extraordinarily, looking for extraordinarily small effects. and they're very challenging. That's why I've spent the last 20 years of my life trying to look at these things. So, at any rate, let me tell you about how we go about doing these experiments. So imagine you have some system with electron spins pointing in arbitrary directions. Our experiment, most of the experiments, polarize the electrons by some interaction with laser light, for example, some optical pumping method that will line up the electron spins, for example, sideways, and you know that's a superposition, spin up and spin down. For technical reasons, our experiment and most experiments apply a magnetic field. That exerts a torque on the magnetic moment of the electron and causes the spin to precess around at the Larmor frequency. Or equivalently, you can think of that as an energy splitting, Zeeman splitting between spin up and spin down. And this gives rise to some sort of spectral line. To look for the EDM, we apply an electric field parallel to the magnetic field. If there's an electric dipole moment along the magnetic moment, that will exert an additional torque, cause these spins precession to speed up, or equivalently cause the energy shift to get larger, equivalently cause the spectral line to shift over. And then what we do is reverse the electric field and look for a change that's correlated in this spectral line or this energy splitting as we flip the electric field back and forth, back and forth, back and forth. So from this picture, it's easy to write down a very simple figure of merit for the statistical sensitivity of an experiment like this. It's just the energy shift due to the electric dipole moment divided by the energy resolution. So the energy shift is the dipole moment times the electric field. The energy resolution is determined by the coherence time of a spin, just from the energy time uncertainty principle, you can think of this, or Fourier transforms. And then it depends on the signal to noise of the measurement. So the bottom line is, to do a good EDM experiment, you want the largest electric field you can get, the longest coherence time, the largest counting rate, and the largest total time of running the experiment. And this is a factor that includes the contrast, that is your ability to distinguish between spins pointing to the left and spins pointing to the right. This total integration time is an approximate constant of nature. It's given by how long a graduate student is willing to sit in the basement and flip an electric field back and forth. But all the other parameters we try to maximize, and in particular our experiment does a particularly good job on the electric field and a good enough time on the coherence time and counting rates. One thing that might seem mysterious at the outset is, I told you want to apply a really big electric field to the electron. But you know what happens if you apply a big electric field to an electron? It flies away. After all, it has an electric charge. So there's a very, very subtle and clever fact, which is that if your electrons are bound in a neutral atom or a neutral molecule, then there is an effective electric field that acts on the EDM that's entirely due to relativistic effects. And this was worked out way back in the 60s by Pat Sandars. This was done with an explicit calculation within the Dirac equation. There have been dozens of papers since. Everybody agrees. There's no mystery that this happens. But there was a mystery for quite some time as to why it happens. And I want to just take you through that. So you can imagine, or you know, that an electric dipole moment interacting with an electric field has this Hamiltonian, D dot E. So the expectation value of the energy shift is if you imagine, you can write it like this because the dipole moment is a constant. Then you find that the energy shift is zero because the average or expectation value of the electric field must be zero. If it wasn't, the electron would fly away. So somehow the charge is redistributed inside the atom, no matter what you do, so that the average electric field experienced by the electron is zero, and therefore there's no energy shift associated with EDM. And this is in fact strictly true in non-relativistic quantum mechanics. It's known as the shift theorem. But in the context of the Dirac equation, relativistic quantum mechanics, that's not true. But well, back in 2007, Gene Cummins and I worked on a review article, and I told him I was always a little baffled by this because no one ever explained what the mechanism was. They did the calculation, they got the answer, but there were no words to help me understand what it was. Gene, in his inimitable way, came back and proved to me that even in the relativistic case, the expectation value of the electric field is zero, even though I and several other folks have written papers saying that it must be not zero because of some magnetic forces. Turns out, even in this case, the electric field is zero. So how can it be that D dot E is not zero? We finally got together with Dave Jackson and figured out what was happening here. So the expectation value of an operator is not always equal to the product of the expectation values, as shown here. This will be true if one of these is a constant, but if both of these things vary with position, then this inequality will be the case. Of course, we know that inside an atom or a molecule, the electric field varies with the position because there's point charges at the nucleus. But we always thought that the electric dipole moment is some constant. How can that vary with position? But the answer is that the electron moves around in the atom, and as it moves, it has a non-zero velocity, and this dipole moment undergoes a relativistic length contraction. So the fact that both the dipole moment and the electric field vary as a function of the position of the electron moving around in an atom is the explanation for how the expectation value of D dot E can be non-zero, even though the expectation value of E is zero. So that was quite gratifying to be able to understand in a heuristic way what the physics was behind these calculations that have been done for decades. At any rate, with that in mind, we use our electrons attached to polar molecules in order to get the biggest effective electric field. The motivation here is that we can apply a very modest electric field in the laboratory, in our case about 100 volts per centimeter, that completely polarizes the molecule. From this simple picture, you can imagine the electron wave function is spread out throughout the molecule, but it spends more of its time on this side of the thorium nucleus and less of its time on that side. So due to this relativistic motion, we end up with an electric field, an effective electric field acting on the EDM, which is quite huge, about 80 gigavolts per centimeter. So effectively, the molecule acts as an amplifier of electric field. We apply 100 volts per centimeter in the lab, and the EDM gets acted on by 80 gigavolts per centimeter inside the molecule. This was the motivation for using molecules. This amplification is something like 600 or so times larger, or almost 1,000 times larger in our case than it is in every atom. And it's simply because the molecule is so easy to polarize. So this is the good news. This was the motivation for using molecules. The bad news is that in order to get a molecule that is sensitive to the electron's electric dipole moment, because the dipole moment is along the electron spin, we need a molecule that has an unpaired spin. If there are closed shells with the spins in opposite directions, the EDMs also pair off and cancel. And molecules with unpaired electron spins are known to chemists as free radicals. They're known to physicists as bloody nightmares. They're really difficult to work with experimentally. And most of our time in the last 15 years has been spent learning how to deal with these chemically reactive molecules. So the particular molecule that we work with, thorium oxide, has a structural feature which is probably unfamiliar to most folks, but I'll just try to give you a cartoonish picture of this now. So we work with thorium oxide molecules in a metastable state where there are two valence electrons that form a triplet state. So there are two electron spins that are lined up in the same direction. That means we have a total spin of 1, and that spin can point along against or perpendicular to the molecular axis. On the other hand, you can take that picture and do the mirror image. So there are actually 6 states that describe the orientation of the spin relative to a laboratory axis, and then the orientation of the molecule relative to the spin. These 2 states, symmetric and anti-symmetric state, correspond to parity states with parity positive and negative. We take these states, if they're very close together in energy, we apply an electric field that mixes them and polarizes the molecule. So we end up with an energy level picture that looks like this, where from left to right, we go from spin down to spin up. From top to bottom, we go from molecule polarized along the electric field, that's the minimum energy state, and molecule polarized opposite the electric field. This maximizes the energy of the molecule. In our experiments, we can either prepare the electron in a state that's a superposition of spin up and spin down, just as I described before. Look for an energy shift between spin up and spin down due to this effective electric field acting on the electric dipole moment. Or we can do the same experiment, but with the molecule prepared in this state, where again it's a superposition of spin up and spin down, but now the effective electric field in the molecule points in the opposite direction because the molecule is pointing in the opposite direction. So now, rather than flipping the electric field back and forth, we can flip back and forth between these two states and reverse the internal electric field of the molecule without ever touching the external electric field. This turns out to be an extremely powerful way to reject systematic effects. Essentially, these two states are mirror images of each other. They have nearly identical properties, such as magnetic moments, and this was a very powerful way to control systematics that I'll tell you about later. So those are the basic features. I'll tell you now about our experiment that we call the ACME experiment. The collaboration between my group from Yale and the groups of John Doyle and Jerry Gabriels at Harvard. The actual experiment is done at Harvard. So I've had graduate students and postdocs and residents up there for the last several years. So the new features of the ACME experiment that are different from anything that was done before. The first feature is that we take advantage of a new technology for creating molecular beams that uses cryogenic pre-cooling of the molecules. This is a technique that we originally were developing in collaboration with John Doyle's group, but then the real key advance came entirely from the work of John and his student Dave Patterson. And they showed that by operating this sort of beam source in the right regime, we could get fluxes that were roughly 1,000 times larger than any molecular beam previously. So that really gave us a big oomph in statistics for these sorts of experiments using free radical molecules. The other new feature of our experiment was using this particular molecular species, thorium oxide. So as I mentioned, thorium oxide has 2 valence electrons. In its ground state, those electrons form a closed shell, a singlet state, so it's actually chemically stable. But it has this metastable state, a triplet state, where there are 2 unpaired electron spins, so we're sensitive to the electric dipole moment. We populate this state by using a laser to optically pump into this state, and then we prepare the spin superposition that we want and probe the state with another laser that emits fluorescence down to the ground state, and we detect these fluorescence photons. So thorium oxide has the largest effective electric field of any molecule that's been used in the experiment so far. It's close to the theoretical maximum for any molecule. This metastable state has a long enough coherence time. It's about 2 milliseconds. That's comparable to what's been used in previous experiments. It has this so-called omega doublet structure that I told you about that allows us to suppress systematic effects. Turns out this particular state has the property that the spin and orbital magnetic moments of the 2 electrons almost exactly cancel each other. So despite the fact that we have 2 unpaired electrons in a triplet state, the magnetic moment of this state is less than 1% of a Bohr magneton. And this means that we're deeply insensitive to any sort of magnetic noise or magnetic systematic effect, which is typically one of the bigger problems with these experiments. There are lots of other technical issues, but bottom line is this proved to be a very nice choice for the molecular species. So here's a quick overview of how the experiment works. From taking through this, we start with this cryogenic molecular beam source, create a beam of molecules that travels from left to right in this picture. The molecules enter a region where they interact with some lasers and microwaves that effectively pumps the Boltzmann distribution of population at different rotational levels into a single level that gives us some signal enhancement. They then enter a magnetically shielded interaction region where, as I described, they're optically pumped into this triplet state that's sensitive to the electric dipole moment, and then they're spin polarized by a laser beam. Then the molecules travel without interacting with anything in parallel electric and magnetic fields where if there's an EDM, the spin will precess around the electric field. And then finally, we read out the spin direction by probing the molecules with a laser beam and detect the fluorescent light in the photomultiplier tubes. So let me tell you a little bit more about how the measurement actually takes pictures of the apparatus. Here's this cryogenic molecular beam source. Here's the vacuum chamber and end caps of the magnetic shields. Here's the light collection optics, so lenses and fiber bundles that carry the light path. These are the electric field plates. They're glass with a transparent conductive coating. The laser beams go right through them. Molecule beam goes between them. Here's the magnetic field coil system that allowed us to apply all three magnetic field components and all first order magnetic field gradients to test for systematic errors. For my LHC colleagues, I put a size scale here. You can understand. Here's the experiment buttoned up with all the magnetic shields around it, some of the optics that are associated with it. And we have full-size optical tables. I would say the optical complexity is comparable to modern experiments with cold atoms. And then our control room, again, for my LHC colleagues, consists of a desk shut in the corner of the lab that we monitor. So, like I said, I'll tell you a little bit more about how the measurement actually works. So the molecules in this picture are traveling from left to right. They're first in their ground state, the singlet state, where the electron spins are paired off with each other. They encounter this optical pair that pushes them into this metastable triplet state where they do the measurement. This results in an incoherent superposition of spin up and spin down, and also molecules polarized up and down. This incoherent superposition travels to a state preparation laser where the linearly polarized laser light, which is a superposition of left and right circular polarization, couples to a superposition of the n equals plus or minus 1 states and pumps that superposition away, leaving behind orthogonal superposition. Spin up and spin down. The other molecular polarized state, we choose to look at one or the other of these by tuning our laser to resonance with either this pair of states or that pair. So you just focus in on the pair that we're looking at. This spin superposition corresponds to a spin alignment. As the molecules fly through the apparatus, they precess in the magnetic field, and they have EDM a little bit more due to the electric field. Where they finally encounter the probe laser, at this point they've evolved into a state with this phase difference phi, which depends on the magnetic field, but also on the electric dipole moment and the effective electric field. So to read out this spin direction in this probe laser regime, we realize we can write this superposition with the phases here as a superposition of the states that interact with either X or Y polarized laser light. So for example, when a molecule is in this state and we hit it with X polarized laser light, if it's in this superposition state, it will absorb a photon and emit fluorescence. You'll see a signal with probability sine squared phi. Because it's in this superposition state, if it doesn't absorb a photon and emit a fluorescence photon, then the wave function will collapse into the orthogonal state. If that happens before the molecules have a chance to fly away, we flip the polarization of our laser beam, and then we excite the leftover superposition. That happens with probability cosine squared phi. Then we take, known as the asymmetry, the difference of these signals over the sum, that's proportional to the cosine of this precession angle, this phase phi. The beauty of this is it's completely insensitive to variations in the molecular flux, which is important because this new molecular beam source is very bright but very unstable. And we were able to show that we got signal to noise that was limited entirely by the shot noise in the photoelectrons of the effect here. So that worked well. And this gives you a typical spin rotation fringe as we can either change the polarization of the probing laser or let the spins precess in the magnetic field. In either case, we get a nice fringe that looks like this. We set the experiment so that we take on a place where the signal or the asymmetry has a big slope with respect to the change in the spin direction. And that gives us maximal sensitivity to the spin when we reverse the electric field. Right, so in a typical molecular beam pulse, we get a pulse of molecules that goes by. The only real data cut we take on anywhere in our data analysis is we require that the signal be big enough to avoid excess noise from backgrounds and the tails of the signal here. So our data analysis is very simple-minded. We say, is the signal big enough? And if it is, we keep it. Then at each time we calculate this asymmetry as we flip the laser polarization back and forth. We bin those up in a very simple-minded, almost undergraduate level data analysis, find the average of standard error, and there's no trickery or complication with the data analysis. So as promised in the experiment, we set that up, we measure the spin direction, and then we start flipping things back and forth. We either flip the direction of the molecular polarization, this internal effective electric field, or we flip the external electric field. We flip the magnetic field. We also flip something that allows us to measure the beam contrast of the spin fringe. At each point, we calculate this phase as the ratio of the asymmetry contrast we measure, and we tabulate the phases that we measure as a function of the direction of the molecular polarization, the direction of the laboratory electric field, and the direction of the laboratory magnetic field. And just bins looking for something that changes sign with the molecular polarization and the electric field. We can rewrite this phase as some offset component, and then various phases that are correlated to the switches that we make. So for example, this one is a phase that changes sign when we reverse the laboratory electric field, but it's even when we reverse the molecular polarization. And you can classify everything in this way. These different things that we call switch correlated phases are related to different physical contributions to our signal. So the electric dipole moment phase is this one, but these other phases serve as diagnostics for possible systematic errors in the experiment. So I'll tell you about systematics more as we go on, but just looking at this EDM phase, the part that has the interesting signal for us, we calculate statistics on this. We did a blind analysis, so we didn't know what zero EDM was until the very last day when we had completed all the other analysis. We took data which gave us, in 40 hours of integration, a statistical sensitivity, standard error in the mean that's at this level, which is about 30 times smaller than the previous upper limit, is our one sigma standard error in the mean here. You can see that this data looks nice and Gaussian, but it's even more striking if you put this on a logarithmic scale. So this is a t-distribution of our errors, and you can see the data is Gaussian out to the very ends of the tails beyond 3 sigma. So it's really statistically unbelievably good data, better than we had any right to expect. So there's no manipulation. We just take the usual standard error in the mean. Where we spend most of our time, we only spend 40 hours taking real EDM data, spend most of our time worrying about systematic errors. So let's talk about that for a while. We knew going in that this EDM phase can have physical contributions not only from the signal we care about in EDM, but also from various other possible systematic errors due to imperfections in the experiment. So for example, we know that when we apply the electric field to polarize the molecules, inevitably some leakage current flows. That leakage current creates a magnetic field. That magnetic field couples to the magnetic moment of the electrons. And when we reverse the electric field, the leakage current will change sign. So we knew that we had to worry about this. Here's the term leakage current magnetic field. Here are some terms that have to do with the non-reversing electric fields in the experiment. When we try to flip the voltages on our electrodes, they don't flip perfectly. So in order to diagnose these, we realized that most of these imperfections appear in some other correlated phase other than the one that contains EDM, but with a coefficient which is much larger than the coefficient in the interesting phase that looks like an EDM. So for example, this leakage current shows up in this phase that's odd in the electric field, but doesn't depend on the molecular internal polarization. And it shows up with a coefficient which is 1,000 times bigger than the coefficient here. Likewise, this one that had to do with non-reversing electric field shows up here in a different phase, but with a coefficient which is 1,000 times bigger. So this is a very effective strategy to look for imperfections of the type that we know could cause systematic errors. And that was great for all the systematic errors that we knew were smart enough to think about, but we didn't trust that we were smart enough to think of all the ones that were going to matter. So the question is, how do you look for systematics that you aren't smart enough to think of? So we had a few strategies for this. The main one is simply to change as many parameters in the experiment as we could that shouldn't affect the electric dipole moment, but might couple to some sort of systematic error. And then not only change parameters, but deliberately screw up the experiment, deliberately amplify something that could be wrong. Make a big non-reversing electric field, and understand anything that changes in the experiment. So these extra reversals, here's a list of them. There are a bunch of them. Each of these can change the effect of things that we were worried about, but would leave the EDM unchanged. Maybe the main message here is that we had more knobs of this sort than any previous experiment, just because of the way the system was built. And one thing which was particularly powerful in our system is that previous experiments, the stronger the electric field, the more you polarize the system, and both systematics and the EDM signal would scale roughly linearly with the electric field. Here, once we applied an electric field of more than a couple volts per centimeter, we really had completely polarized our molecule, and we were able to run an electric field that differed by a factor of 5 or so. And our EDM effect we knew had to be 2 electric fields, but many systematics would change with this if they were contaminating our data. So under these extra switches, here's what we see. Everything is consistent with no significant change with any of these, including the magnitude of the electric field. So that was encouraging, that there's no systematics that couple to these knobs that we can turn. But then, as I mentioned, we also went through and had a very long list of imperfections in the experiment that we worried could cause systematics. We intentionally amplified them and looked to see if it changed our number for the EDM. And again, we didn't know what 0 was, but we could see if the number shifted from whatever blind offset we had imposed on it. So whenever we amplified one of these imperfections, we didn't fold that into the EDM limit, because we figured something was wrong deliberately. One of the things we quickly ran into was we had so many of these that we had to think about how big does an effect have to be meaningful. So here, for example, is a list of about half of the parameters imperfections we deliberately amplified, and then various correlations with the phases that we made. And the color here corresponds to how many standard deviations away from 0 the change was. And we realized we had to make a statistical distribution of our systematic error checks because there were so many of them. It was inevitable that some would be 3 sigma away, and that actually wasn't surprising at all. So unlike our real EDM data, this distribution was pretty Gaussian, but there are outliers in the tails, which you can't see here, but they're shown, for example, with the red dots here. These are big enough outliers that we knew that they meant something real, I think. And the few outliers, we were ultimately able to understand them all and or control them all at a level that didn't concern us. So just to give you a sort of idea of one of these systematic errors that we did have to understand and spend some time controlling, there was one that came about when we deliberately amplified the non-reversing electric field, which we later realized required our laser beam to have an incorrect spatial profile and our laser beam to have a polarization or an ellipticity that was different at different places in the laser beam. So this is experimentalists in more physics will recognize this is a pretty nasty combination of things. And we spent several months figuring this out, and then at the end of that, we threw everything away and started over. But to give you a sense of what was happening here, our molecules fly through these electric field plates that are transparent. Our laser beams are shining through them. These are very high power laser beams, several watts of power. The electrodes were carefully made, but they still had a very slight absorption of the laser power. This heated up the electrodes where the lasers went through. That caused a thermal expansion. That thermal expansion causes stress. The stress induced a birefringence, and that birefringence caused the laser to have an ellipticity that was changed as a function of the position in the laser beam profile. So that alone was not enough. In addition, if the laser beam profile was not simply a square pulse, but actually had a Gaussian shape, as our lasers naturally did, this caused some non-adiabatic evolution of our molecular states that created what's known as an AC star shift, a light-induced energy shift in the molecular phase. But that depends on the lasers being not in resonance with the molecular transition exactly. But then if you couple that to the fact that if you have an electric field that causes an energy shift due to the ordinary Stark effect, then if you reverse the electric field and its magnitude changes because there's a non-reversing component, that causes a Stark shift, which is correlated both with the sign of the electric field and the molecule is polarized along or against the electric field. The Stark shifts have the same magnitude, but they go in opposite directions. So the coupling of all of these things together caused an EDM-like signal in our precession phase. All of these things were going wrong at the same time. We diagnosed this by deliberately amplifying this non-reversing electric field and saw this effect show up. So to get rid of this, we had to suppress our non-reversing electric field. We went in and were able to use molecular spectroscopy to do careful measurements of our electric field. We saw the non-reversing component was no more than a few millivolts per centimeter everywhere. And in addition, to verify with the molecules an independent measurement of a slight curvature in our electric field plate that caused the electric field to change with magnitude. In the end, when we applied a big non-reversing electric field, when we started expanding the effect, we had a big systematic error. In the end, after we corrected things by reducing the stress induced by refringence, we could apply a gigantic non-reversing electric field and see no observable phase shift. Then knowing that our non-reversing field was very small, only a few millivolts per centimeter, we could set a limit on how much this effect leaked into our EM data. As anyone who's done this sort of experiment knows, in the end, the product of your years of work is a systematic error table, like this one. There are lots of components here, but maybe the takeaway message here is that we applied very small shifts from any of these effects, small compared to the uncertainty in the shifts, which is driven just by our statistical sensitivity, how long we integrated. And the overall statistical error bar in our data set was still bigger than our systematic error shifts and uncertainties in the systematic errors. So altogether, it's fair to say we're dominated by statistical error in this experiment. And this bottom line is, here's this plot that I showed you before of predictions for the EDM in different models. The previous limit from Gene's experiment here at Berkeley and Imperial College. Here's the result that we got. It's consistent with 0. We use that to place a new upper limit on the electron EDM, which is about an order of magnitude better than what had come previously. And you can see we're really deeply cutting into this parameter space, these theoretical predictions, and yet still no electric dipole. So just to give you a sense of what does this mean in the context of particle theory. So here's one, I would say, typical paper from the theorists in the field. This is talking about supersymmetric models that have not been ruled out yet by the LHC, and doing a sort of Monte Carlo in supersymmetric parameter space of what would predictions for the electron and the neutron electric dipole moment be. The previous limits on the neutron and electron electric dipole moment had ruled out about 2/3 of the supersymmetric parameter space that had survived the LHC already. And our new limit cuts out about another 2/3 of this. So really we're knocking out something. EDMs are knocking out about 90% of the supersymmetric parameter space, given the particular assumptions that are in this model, but they're fairly generic assumptions. Here's another view of this. So this is a paper that talks about whether what we know about particle physics in the year of the LHC and our EDM measurements is consistent with these ideas about the naturalness of supersymmetry as a way to solve the hierarchy problem. And you can see the LHC limits here say that there are limits for superpartner masses that have to be above the blue lines. Dark matter experiments say these superpartner masses have to be below the red lines. Green is what the theorists would like to see. And you can see the biggest problem here is the Higgs mass is actually lighter than it should be, and it's indicating that superpartner masses have to be heavier than seems natural. This was from previous EDM limits. Our new limit pushes this well above the scale of naturalness for the supersymmetric partners of electrons and neutrinos. So again, naturalness is in the eye of the beholder, but this gives you some sort of sense that we're pushing in a direction that's competitive with what's being done at the LHC. Something else that I found sort of interesting was it turns out that this sort of limit here assumes that there are EDMs that arise at the single loop level in supersymmetric theories, but they can also appear at the two loop level through diagrams like this. And it turns out that our EDM limit sets a very strong limit on the extent to which a top quark can couple to a Higgs boson via CP violating coupling. So this shows couplings of the Higgs to the top quark, both the CP even part here and the CP odd part here. So this is determined by the LHC through Higgs production measurements to be this sort of banana-shaped region. Our EDM measurement says the CP odd component of this top Higgs coupling has to be within this tiny blue band. So it's really a real method in particle physics. So I'll just skip that. It's a little more speculative. So the thing to keep in mind here is that we're far from done. So we think that there are really dramatic improvements in this experiment. What I told you about was very much the first generation. We have a number of things that were very range from basically no to being pretty confident are going to get us better statistical sensitivity over the next handful of years. We think in the long run it may be possible to get 300-fold improvement in statistical sensitivity. Right now we're working on an improvement, a second generation to get an improvement of about an order of magnitude in the square root of the counting rate. So to summarize that, again, here's the limit that we just published. We're now working on the next generation where we project the statistical sensitivity about an order of magnitude further. The systematic errors that we know about should be under control at that level. The ones we don't know about, we'll find out about and see if we can control. And then in the long term, we think we may be able to push this technique perhaps this far, though this will take longer, obviously. So before I end, I'll just point out, this was done, again, a collaboration between my group of Jerry Gabriels and John Doyle at Harvard. We had a really tremendous group of students and postdocs who worked on this. My student Amar Butha, who came up with, along with me, a lot of the original ideas for the experiment, and then really this tremendous group of coworkers. It's been just incredibly fun to work with these folks on this experiment. Real challenge and beautiful results. So with that, I'll just leave this plot up and thank you for attention.
I have a question. So admittedly, you started out with sort of a cartoonish kind of description of the electron as a point particle. So what I'm wondering is how the theory of the experiment play out if you assume a string theory assumption of the electron. And what does that mean?
Right, so I have to say, I don't believe I've ever seen any theoretical discussion of EDM induced in string theory. At least to my knowledge, it's still too many steps removed from observable quantities like this one. But I don't know, maybe there are theorists in the audience who can correct me about that. But to my knowledge, all the discussion about EDM has typically been in the context of extensions to the standard model. sometimes those extensions are motivated by string theoretic considerations, but there's certainly, to my knowledge, no calculation based on string theory of what the EM should be.
If you keep pushing the sensitivity and keep getting zero for the dipole moment, that's very relevant because you rule out these models. But will you be surprised? Or were you surprised when you got zero in 2013?
Yeah, you know, it was a pretty dramatic moment when we unblinded the data, because I think about half of us really believed that it was going to be non-zero, and about half of us who have done this before were so jaded that we said it was But there was honest tension in the room because we really didn't know, and I think it's going to be that way, you know, for a while now. The disturbing thing is that as we push further and further here, we start to get to the point where the mass scale that we're sensitive to is really well beyond the electroweak scale. And once you push well beyond the electroweak scale, there's no guidance for what scale is a relevant scale. And until we have some guidance, then I think hope will start to fade rapidly after we push the next couple of orders of magnitude.
Just one thing is to remember, this is a combination of two variable interface. And so, in some sense, it's just controlling the size of this spectrum. If it is there, we didn't post that in a different way. But if independent experiment finds a new particle, and this experiment is using and not finding anything, right? You really have to learn that there's some mechanism it simply resolve. Again, it's not that super simple thing, but it's
Absolutely within the realm of possibility. But by the same token, I'll point out that it's well within the realm of possibility if the new mass scale is somewhat above the reach of the LHC, and that new mass scale includes CP violation, we're one of the few games in town that plausibly could make that sort of discovery. So that's what keeps us motivated from day to day as we flip our electric field back and forth.
yeah, the other thing is really
Yeah.
Yes.
If you switch to a different molecule, maybe you would have a smaller effective electric field, but maybe you wouldn't have to have 10 lasers, and maybe that would reduce some of the uncertainty. Is that something you think about?
Yeah, so we pretty carefully went through the list of possible molecules. So the 10 lasers at this point is a solved problem. And really what's, at this point, we're limited by the flux of the molecular beam and by our ability to detect the molecules efficiently. And this very optimistic blue line there corresponds to detecting with 100% efficiency, which we think we know how to do, and also pushing the molecular beam flux to a level that we've seen for a while before something broke. But both of those things, you can't do better than 100% efficiency, and we have never made a molecular beam brighter than the one that we had for a while until it broke. So, of anything. So we think that's what we do. What is the future, I think, beyond that, if there needs to be a future beyond that, is now our group and a few others have started to show how to laser pool and trap molecules. And that gives you the potential to have much longer coherence times, and that could change the game substantially. But that's a technology that still needs a lot of development.
Somewhat facetiously, the electron has no charge.
Well, that's not obvious, actually. So, for example, the neutron has no charge, but it can easily have an electric dipole moment. It's predicted in the same theories. Yeah, sorry, I'm not sure what you're referring to there. Sorry, I can't quite picture. Maybe we can talk after it. Yeah, you can put me to the slide. Yeah.
So are there any other experiments that will be using different molecules, or is it easy to switch them out in your experiment for some other type of schematic check, even though you solve the laser problem?
Right. So it's definitely not easy to do, although this is something we talked about. If God forbid we see a non-zero signal, one of the things we could certainly do is switch to a different molecule with a different effective electric field. But in the meantime, yeah, there are, I guess, now 2 competing groups that are using different types of molecules and either slightly or radically different techniques to make the same sort of measurement. So Eric Cornell's group at Gilla is doing this with cracked molecular ions. The Imperial College group here, Ed Hines' group, is using ytterbium fluoride molecules which have a single unpaired valence electron. So those experiments, all the systematics are utterly different. The sensitivity is quite different. And as I tell them frequently, I'll be very pleased for them to verify our first discovery of the EM.
Yes. Okay, I was just kind of interested, you said, because you said that your real, this uncertainty right now is coming from PMTs.
Yeah.
What kind of relationship is that?
Yeah, so we bought a sort of beta testing prototype PMT that had 4 times higher quantum efficiency, which probably broke, and they won't sell us another one of that kind. That's our relationship with Hanmax. But you know, what we really, so that particular PMT was developed for the Hess cosmic ray telescope, and essentially we have to piggyback on some larger experiment that's cost effective for them to develop 2 things, and we're eagerly awaiting them to make the next generation of Hess PMTs work for us. Oh yeah, the green doesn't depend on any new technology, and actually the blue doesn't either. It depends on some atomic physics tricks to essentially get more photons per molecule, even though we can't collect the photons very efficiently. But even better would just be better photons.
What other questions?